Hello. We're going to be looking at Chapter 11 today, and this has to do with chi-square testing. We will be using nominal data, and there are several different forms of the chi-square test, so we'll help you to try to identify which is which and when to use each of those particular types of tests. The tests will come from what we call contingency tables, and those are just tables that have two directions to them, like rows and columns essentially. And then depending on what we get as results from the chi-square test, we also have to learn about the Marsuglio procedure, which will help us to determine which of the several proportions may be different. Okay. Whenever we have more than two populations, multiple populations, proportions, that's when we're going to use these contingency tables, and they're also sometimes called cross-classification tables, and chi-square is the main form of analysis that we can do with these kinds of tables. So here's an example. Let's say we're talking about left-handed people, and we're looking at gender, which would be sex, male or female, and we're trying to say, does knowledge of one help me to predict the other? If they're not related, or there isn't any relationship between them, the proportion of males that are left-handed should be the same as the proportion of females that are left-handed. Since we only have two categories, right and left, and male and female, for each variable, that's what we call a 2-by-2 table. And it's a special form of contingency table. If we have a sample of size 300, maybe this is what our data might look like. Notice in the lower right-hand corner we have the number 300, which is the size of our sample, and then we've taken a sample including both males and females to find out what their hand preference is, whether it's right or left-handed. So our sample size is n equals 300, one sample, and what we want to know is about the proportion of males and females that are left-handed. The basic idea here is if there isn't any difference between males and females, we would expect the overall proportion to be the same for males and females regarding being left-handed or not. So for instance, we have 120 females and 120 males, giving us our total of 300. Of those, 36 are left-handed and 264 are right-handed. So this is the hypothesis we're going to be working with here. We're looking at proportion data, which means percentages. There's no means, there's no standard deviations. So when we're doing this kind of test, the first thing you might think is, gee, it doesn't look like we have much information. That's a pretty good indication. It's probably a proportion test that we're going to be doing. The null hypothesis for chi-square is always going to be, if we have two populations, always going to be proportion 1 equals proportion 2 is my null. My alternative is proportion 1 is not equal to proportion 2. So in that sense, it's always a two-tailed test. We can't do a one-tailed test. If you remember the z proportion test that we did before, that could be either one or two-tailed. Here it has to be a two-tailed test. So if the problem wants to know if there's a difference, we could possibly use this test or the z proportion test. However, remember, z proportion assumes a normal population distribution, whereas chi-square does not. So if we don't have a normal population distribution, we need to use chi-square. If it is normal, then we would use z. We still have nominal data for both types of tests. We still have independent random samples for both tests. And so the main difference is it one-tailed or two-tailed? If it's one-tailed, it has to be z proportion. If it's two-tailed, could be chi-square or could be z proportion, depending on whether we have a normal distribution or not. Okay? If the null is true, which the null says the proportion of females who are left-handed is equal to the proportion of males that are left-handed, then that's what we're going to assume while we're doing our test, is the proportion is no different. The alternative is the proportion would be different between the two groups. That means then, if there is no difference, we would apply the same proportion to both groups. I'll show you what I mean by that in a minute. Here's the formula. Chi-square equals the summation for all cells of the frequency observed minus the frequency expected, difference squared over frequency expected. Observed values are always what I found in the sample. Expected values are based on the assumption that the null hypothesis is true. So you're going to have to find the expected values for your chi-square problems. The observed values are going to be given in the problem. So whatever is given is the sample or the observed data, and then we'll show you how to find the expected values so that you can complete the problem. Okay, for a 2 by 2 type of chi-square problem where we have 2 rows and 2 columns, we will have 1 degree of freedom. The formula is rows minus 1 times columns minus 1. Since I have 2 rows, that'd be 2 minus 1 times columns minus 1, which is also 2 minus 1. That gives me 1 degree of freedom. So anytime I have a 2 by 2 table, I have, in other words, a proportion problem with 2 populations, then it's going to be 1 degree of freedom. Each cell in the table has to have expected frequencies of at least 5. Okay? We'll show you how to find out whether that's true or not. That's just a rule for chi-square. If we have expected frequencies which are real small, it's going to give me a real big value for chi-square, which might cause me to reject the null when I shouldn't be rejecting the null. So expected values have to be at least 5. Observed values can be anything. Okay, this is what the chi-square distribution looks like. It's not normal, remember, and since I'm squaring the difference between observed and expected and adding it up divided by the expected, I can't have a negative value for chi-square. The minimum value is 0. And the higher the value, the more likely it is I'm going to reject the null, just like analysis of variance. Okay, because it's a squared difference, it's got to be positive. High values will cause me to reject the null. Low values will be close to 0 and cause me to fail to reject the null. If my calculated value of chi-square is greater than the critical value that I find in the table, I'm going to reject the null. That's out here in the shaded area on the end. If it's close to the 0 value or near the x and y origin point, then I would fail to reject the null. Okay, what we're going to do in this problem, or one way to do it at least, is to compute the average proportion. So that means we're going to take x1, which is the number with the characteristic from sample number 1, and add the number with the characteristic from sample 2, so that'd be x1 plus x2, divide by n1 plus n2, which is the combined sample size, and that's going to give me what's called p bar. That is the average proportion of both males and females that are left-handed. That figure in this case would be 12 plus 24 divided by 120 plus 180, which gives me 36 over 300 or 0.12. That is 12% of all of the sample was left-handed. A little different for each group, but what we care about is the overall average proportion. So to find my expected values, one way to do that is to simply take that average proportion and multiply by the sample size for both males and females, and that will give me the number of males and females that I would expect to be left-handed if the proportion is the same. Okay, so here's that process. If I take 0.12, which is the p-bar, average proportion, multiply by 120, multiply by 180 for females and males, these are my expected values. 14.4 for females, 21.6 for males. That is 0.12 times 120, 0.12 times 180. So those are my expected values for 2 of the cells in my table. So I go up here and I put those in the table. You see those are in the first column here, corresponding to left-handed. And the other proportions, the other expected values that I need to find, can also be found in a couple different ways. Either I can take 1 minus the 0.12, which would be 0.88. That means 88% of people are assumed then to be right-handed if 12% are left-handed. So I take 0.88 times 120, 0.88 times 180. That would give me the 2 expected values that go in the other column of the table. Those are 105.6, 158.4. if I add this value and this value, 158.4, 21.6, I'll get 180. If I add 14.4 plus 1056, that'll give me 120. The row and column totals for both observed and expected have to add up to the totals. Okay? So you know you have the right answer when they do that. If you find one expected value, if it's a 2 by 2 table, you could subtract to find the other expected value because you know it has to add up to the total. Okay, here's another way to find expected values. Row total times column total divided by n. So for this cell right here, I would take 120, which is the row total for the first row, times 36, which is the column total, and divide by 300. That would give me 14.4. So if you find it easier to do it that way, feel free to use that approach. Row total times column total divided by n. For this cell over here, it would be 120 times 264 divided by 300. Okay, so I'm ready now to find my chi-square value. To do that, I take observed minus expected for each one of the cells of the table, 12 minus 14.4, difference squared over expected, which is 14.4. So that's the first cell. I can do these in any order that I want to as long as I do all 4 cells. So if I go to the next one, whoops, I'm sorry, let me back up a minute. If I go to the next one, I'd have 24 minus 21.6, difference squared over 21.6. Same thing here, and I'm going to have to do 4 different numbers because I have a 2 by 2 table. All of those 4 squared differences divided by expected added together gives me my chi-square value. That value is 0.7576 in this case, which appears to be a pretty small value for chi-square. We're going to have to look in a table, find out what the value is, and then see whether it's small enough that we can fail to reject or not. But that seems to be a pretty small number. Okay, so our calculated chi-square or test statistic is 0.7576. To find my critical value, what I'm going to do is go to the chi-square table in the back of the book. And I'm going to look for 1 degree of freedom, because remember I have a 2 by 2 table. So that's in rows minus 1 times columns minus 1 gives me 1 degree of freedom. Looking at the table, this is on page 556. What I'm going to do is stay in the row that corresponds to 1 degree of freedom, which is the first row, and go to the upper tail area, which corresponds to 0.05. And I have 3.841 is the number I find in the table. 3.841, that's my critical value. So what that means is, if I get a value greater than 3.841, I'm going to reject the null. If I get a value less than that, I will fail to reject the null. So here's my 3.841 on the diagram. My calculated value, remember, was 0.7576. Goes over here. So therefore, I will fail to reject the null. Okay, what that means is, because my calculated value is less than the critical value, I would not reject the null, which says then there's not enough evidence to say there is any difference in the 2 proportions at the 0.05 level of confidence. Okay, so let's kind of recap for just a minute, because I don't want you to forget what you already know relative to your 6 steps. For all chi-square problems, we still want to use our 6 steps. For the last problem then that we just did, going to work through that one a little bit just so you can see kind of what the steps are again. All right, so step 1 is the null and alternative. And remember, this problem was called a chi-square test for 2 populations, and so the null hypothesis is proportion 1 equals proportion 2. It has to say pi 1 equals pi 2. That's the only hypothesis we can have for a chi-square test with 2 populations, because I can't have a one-tail test, remember. The alternative says proportion 1 is not equal to proportion 2. Step 2, n1 equals, if we remember the data, we can go back to the data if we don't quite remember. Okay, here's my observed and expected values that I had in this portion of the table. And what I want to do now is I want to go through my several steps. So my sample size was 300. I only had 1 sample here, 300 observations. And what I would say is that, so I just say N equals 300. Actually, I would not do that. I'm sorry. Let's do it this way. Let's say N1 equals 120, N2 equals 180. That's the number of males and females that we had in our two samples. Okay? And then we're going to continue with our 6 steps. So let's see. We want to go to Smartboard. Okay, so N1 we're going to say is 120. N2 equals 180. That's the number of males. And pi alpha equals 0.05. Step 3. This is a chi-square problem. It is a chi-square test for the equality of two proportions. Okay, the reason I know this is because I have nominal data. That means we're talking about percentages. I have two populations. I have independent random samples. Okay, and all of my expected values, remember for this kind of test, have to be at least 5, greater than or equal to 5. Okay, in order to make this a valid test, it is a two-tailed test, which is good because remember, if it was a one-tailed test, I would have to use z proportion. So it's two-tailed. Step 4, my critical value. Critical value, chi-square equals, remember, 3.841. That's based on 1 degree of freedom and an alpha level of 0.05. So I looked in my table and that's where I found that value. Step 5 was when I calculated the value for chi-square. Remember, I have to find my expected values first, and then I can calculate chi-square. Chi-square was equal to 0.7576. So it's a pretty small number there. That was my calculated value of chi-square. If I put it on my diagram, remember, here's 3.841. Here's 0.7576 over here. Here's my rejection region. So I'm going to fail to reject the null. So now I'm ready for step 6. In step 6, that's what I would say. Fail to reject the null. Okay, I've got 0% confidence because I failed to reject the null. And what I think is proportion 1 equals proportion 2. Okay, I'm not going to change policy because I failed to reject. Not going to change policy. And the only other question is my answer likely to be sensitive to alpha? So to figure that out, I just look at the two numbers. It doesn't look very likely to me because I've got 0.75 here and I've got 3.841. They seem to be pretty far apart. It's going to take an awfully small value, awfully large value of alpha to be able to reject here. So if I wanted to figure out my p-value, which is one other thing I could do, what I would do is I'd look up my step 5 value and I'd look under 1 degree of freedom in the chi-square table. And I'd try to get as close as I can to that calculated value. All right, so that value is found. Let's see, chi-square table, because it's a chi-square problem. I'm trying to get as close to 0.7576 as I can in the row that corresponds to 1 degree of freedom. So all I can say based on this table is it's between 0.102 and 1.323, and that corresponds to 0.75 and 0.25. So I'm going to write on my diagram here, P is between 0.75 and 0.25. Okay, if that's the case, that says that I'm not going to be able to have very high confidence in any decision to reject. The most I can have is 75%. Least I can have is 25%. So it's 1 minus each of those values. So it's not sensitive to alpha, which is what I wanted to know. So what does that mean? That means the proportion is no different. Knowing whether they're males and females doesn't help me to predict. whether they're going to be left-handed or not.